Garcia Morin from the Stephen Castle Lab, and her presentation is titled Application of a Novel Serine Ligation to Macrocyclic Peptide 2-Cyclin C. Whenever you're ready.
Ready. So hi everyone, I'm going to talk about a novel serine ligation that was developed in our lab, and it's applied to the synthesis of the peptide 2-Cyclin C. So to start with that, I'm just going to explain a little about peptide ligations. So in the normal synthesis of peptides, when we are trying to synthesize peptides or proteins, the length involves a lot of problems. So every time that we are trying to include another amino acid, we get side reactions, we get byproducts, and we have like epimerization. That's why it's needed to use peptide ligations, because they allow to conjugate unprotected segments of peptides to make these long peptides or even proteins. And one of the main ones is the native chemical ligation. It's a huge ligation that it has been really important in the synthesis of peptides. And what it does is bonds two unprotected segments of peptides to create like bigger ones. And one of the things of this native chemical ligation uses is cysteine, and the key reaction is a trans-thiosterification and sulfur to nitrogen acid transfer. But as we know, it has some limitations, and the limitation is in the cysteine, because the key feature of this ligation is the using a cysteine residue in the middle of the peptide that we're trying to couple. And that's a limitation because not all the natural products that they have peptides contain cysteine. It's not a really common amino acid. That's why it was necessary to develop other kind of chemical ligations. In this case, serine-threonine ligation. Serine and threonine, they are more common amino acids in natural products and in other peptides, and they were trying to do kind of the same approach. This Dr. Lin 2010, he said that it was they were using a serine-threonine residue in one of the parts of the peptide, and the other part uses a salicylaldehyde ester. Here's when we get with the problem. Even when this chemical ligation it works, the synthesis of this salicylaldehyde ester it includes like multi-steps. They have 4 ways to synthesize it, but they also saw that it's not really compatible with some of the amino acids. One of them is including proline. So when we have proline in the peptide adjacent to this ester, it doesn't work really well. The reactions are pretty slow. So what even when it works really well, it still has some limitations. That's why in our lab it was proposed a new peptide ligation that it includes serine, like using this approach, like serine is more common in the peptide synthesis, and we are also trying to use a carboxyl alkylation. And the key feature here is that we are using a C-terminal as a nucleophile to reduce epimerization. And you can ask, like, well, how? It's because in the normal synthesis, when we are using the C-terminus to bond with the N-terminus, it acts as an electrophile. When we get rid of this hydrogen, we have an activation of the alpha carbon here, and that promotes the epimerization in this carbon. But in this one, we're using this as a nucleophile. So this one is acting as a nucleophile, and the carbon active is going to be in the other side of the molecule. And this project was tested in a large scale by Dr. Regina So, and she showed that it worked really well with most of the amino acids, including proline. But then we wanted to see if it works in a molecule that is more complex, and this is 2-Cyclin C. 2-Cyclin C comes from the guanabana. I don't know if someone of you have tried this delicious water. And this plant, specifically the seeds, they have like anti-tumor activity, and they are also tested for antibacterial activity. So this molecule contains 2 of the key features that we need in the proposed ligation. It has a serine amino acid, that is the one that we needed, and it's attached to a proline. So we can test that this method can apply for peptides that they are more complex and that they have like the proline amino acid that it has been like problematic in other reactions. So, and another thing, it's a macrocycle. So macrocycles they are kind of, as Grace explained before, they are kind of challenging. So now what we were doing, our work is develop these two segments that we are gonna bond with this ligation. And we are having this first one that is a pentapeptide. This pentapeptide is just created with solid phase peptide synthesis. And this one includes just, we are using the synthesizer, we use FMOC protected amino acid, we just put all together soft cleavage benzylation to get this C-terminus protected, and that's all. We are using alloc amino acid at the beginning of this one in the residue that we're gonna use for the oxygen-nitrogen transfer, but we are open to try other groups, other like protecting groups to see how it works. The other partner coupling that we are gonna use is this dipeptide. And this dipeptide is used with common peptide coupling. It's made on solution and it's hydrolyzed so we can have like the carboxylic side attached to the proline protected. So once that we have these partner couplings, we have the whole synthesis. And this is kind of cool because we are having this pentapeptide, number 3 that I already mentioned before with this dipeptide, and we are using the key reaction in this serine ligation that is a Mitsunobu reaction. This Mitsunobu reaction is going to allow us to have the formation of the ester between this carboxylic, between between this carboxylic acid and then the OH for the serine. So we need a carboxylic acid and an alcohol, right? So once that we have this one in the Mitsunobu reaction, we're gonna have our heptapeptide with an ester. This ester then is gonna be deprotected in the site of the allo group that I mentioned before. We can use drop of TO group. We are still experimenting in that part. And once that is removed, we're gonna have the free amine. This free amine is gonna be performed by the oxygen-nitrogen transfer here, that we can get the normal peptide bond that we can see in the natural product and the one that is required. Then, after the protection with palladium black and a hydrogenation to remove all the benzylation and CBC groups that we have in the molecule, and a soft cleavage to remove the bulk protecting group that we have in the tryptophan residue. And finally, once that we have all our molecules deprotected, we do a macrocyclization. One of the challenges in this last reaction is we have a lot of deprotected groups and we want to get an intramolecular reaction instead of intermolecular. But it was a method for Dr. Brimble design that allowed us to get this macrocycle, and we already have the macrocycle. We could purify it. We are just trying to optimize the yield. But the macrocycle was formed, and last year it wasn't great, but we have some drawbacks. So we are trying just to improve the yield and to know how much it is gonna get us. The other thing is, as I mentioned, all of these steps, they are an optimization. These steps, they are already performed, and the macrocyclization was performed too. And our future work consists in the completion of this total synthesis of tunicycline C. We want to finish the characterization of this product because, as I mentioned, the preliminary data is already characterized and ready. So we just want to see how this application of tunicycline C can be done, and of course optimization and increasing the scope, like trying with longer peptides or with different living groups. And I just want to thank Dr. Castle, Dr. Regina So, who was the one who was working in this preliminary data and the scope, and Katia and Braxton, that they have been the undergrads, that they have been working in this project, and I'm open to any questions.
You mentioned that macrocycles are challenging to, specifically to close. What makes those difficult?
Yeah, so one of the first things that we can see in this molecule is we are trying to create this amide bond, right? We have this glycine here. I'm just using this as a reference so you guys can see where it is closing. We have this glycine amino acid here with the OH, the COH, and then we have this NH2. So then they are closing in this part, and this amide bond, we will expect that the molecule react with itself, but then if you have a lot of molecules here, they can react with other molecules. like doing this intermolecular reaction, that then it also can react in any other NH sites and create all these byproducts. So that's the main part, trying that the molecule doesn't interact with the friends and the stages interacting, being more selfish, and I think just in that specific site.
So going off of that question, have you found evidence of it like polymerizing, or has the rate been like unimolecular generally faster, so you get a clear, definite, this is the majority of the product, or majority of the product being the cyclized version?
Yeah, thank you, and I'm glad that you asked that because I forgot to explain. We are doing the purification but HPLC. So during the HPLC run, you can see all the products that you're forming. We have huge products like the peaks that they correspond, like the first ones that they come is the DIPEA and all these products. But then we also can track, that we don't want to trash them. We can track the mass of all the byproducts that we are forming, and we can see all the peaks. So my first run that I did, it was like it was between 10 to 60% to try to get all the peaks, and by mass spec I could check what is the mass, and the mass correspond for some of them. In this case, this reaction is specifically doing for in a really slow pace. We are doing 0.5 milliliters per hour. So we are trying to do it like pretty diluted. So we try that the interaction, a lot of stirring, so they don't hit each other, and we have this ovolysis effect, trying to avoid this. So we didn't have a lot of the other product, but it is present, and you can see, and it has seen in other, even in the small reactions. That's why we believe that it's important to have maybe chemical ligations in order like to avoid these side reactions that they are common because of the nature of these carboxylic and amine sites.
So I'll follow up on what Dylan said. So he said that in general, intramolecular reactions are faster than intermolecular reactions. Is that the case when you're making a macrocycle?
Okay, repeat the question.
When you're making a macrocycle, is the cyclization, the intramolecular amidation, generally faster or slower than if you were making an intermolecular?
I think that this is lower.
Right, so with macrocycles, it's usually slower, in contrast to if you were making a 5-membered ring or a 6-membered ring. And so why is it slower to make a macrocycle?
Well, it's also because when we have, I'm not sure about this, but I have been thinking of the folding states that we have in the peptides.
Yes.
And like the peptides, they have these, they promote some folding states. So because of that, because of the promotion of these folding states and for the interaction with the hydrogen, but in the interactions that we have with other molecules, like the intermolecular way goes faster than intermolecular. So trying to get this side closer to this one is not as easy because of these folding states.
Right, so just kind of the final follow-up there. So 7, in the low energy conformation of 7, how close are the amine and the carboxylic acid going to be to each other?
But, well, not really close.
Exactly, yeah, so they're gonna be further apart, and therefore you're gonna pay an energy penalty to get those closer together.
With that deprotection step, you kind of mentioned that there's some challenges with having everything deprotected for the following step. Have you explored any like using different protecting groups to do any like selective deprotections there?
I'm doing 2D protections, this one or this one.
Okay. I guess I didn't realize it was 2.
But I can go to the 2. I have tried.
Okay.
I have tried everything. With this one, the other group we have tried. Initially, I tried, like Lily had one that it used the tetrakis palladium, that is the most common one to do the alloc protection. I have used that one before. It didn't work, but I'm not sure if it's because of the method or because this allo group is very hindered. Like it works more when you have the allo group at the end than when it is in the middle of the molecule, and this one is pretty hindered. The second thing, this with palladium black was the only one that it worked. I use palladium carbon, that is the normal one, and I use different days, and I'm using 500 psi 6 days.
Yeah.
Forever, take you forever, but it really worked and it gave you just the main product. So
Okay.
this one, it was like already explored, and I think that these are best conditions. For this one, we are still exploring that part and mostly trying to see if we can get a better living group in this case.
What fundamentally makes the ligation difficult when you have the serine and the proline groups compared to just other serine and other amino acids next neighboring it?
In these ones?
Yeah.
Yeah. Well, I think that one of the things is like, I also didn't mention, but these are the high ester hydrolyzed very easily. So having like the proline there, proline is one of the most rigid amino acids too.
Mhm.
So it also increases the rigidity of the peptide site that we have, and also doesn't have the hydrogen. So the lack of that hydrogen avoid the hydrogen interaction. So same problem that we were mentioning. We keep it apart. Also, proline promotes C turns.
Thank you.
You're welcome.